Hello there, amazing people. I'm back with yet again another past question that we're going to be doing justice to. So, on the screen right now, we have a question that starts off by saying the reaction between aluminium powder and iron 3 oxide is used in the rail industry. So, I have the picture of a train over here and some tracks under it. Okay, the tracks provide a platform upon which the train can move. So we have some questions we want to answer as far as this concept is concerned. Question A says write a word equation and a balanced symbol equation for the reaction that takes place. A word equation and a balanced symbol equation for the reaction that takes place. What reaction? The reaction between aluminium powder and iron 3 oxide. Aluminium powder and iron 3 oxide. So the word equation is going to look something like this. We have aluminium plus iron 3 oxide. So what is this reaction going to produce? So first things first, we have the first metal standing alone. This is aluminium, it's a metal. And we have the second metal, which is iron, standing in a compound. So the next question to ask is between aluminium and iron, which one is more powerful or which one is more reactive? In order to answer that question, we would need to check out our reactivity series. So let's backtrack a bit to check it out. We have aluminium and iron. So the position of aluminium is over here and the position of iron is some steps below it. So that confirms to us that aluminium is more reactive than iron. So aluminium would displace iron from a chemical reaction. So we have aluminium. Let me write that down one more time. Plus iron 3 oxide. So what happens is aluminium comes over here to displace iron from this compound. So iron stands alone. So we have iron plus aluminium oxide. That is the word equation. So let me write it on a platform that allows us for more space so we can answer that question. Write a word equation. So let's go ahead and write the word equation. We have aluminium plus iron 3 oxide. That gives us aluminium oxide plus iron. This is a chemical reaction that is used in railways to produce railway tracks. So we've written the word equation. Now it's time to write the symbolic balanced equation. So let's do that very quickly. Aluminium has the symbol Al. Iron 3 oxide has the formula Fe₂O₃. So aluminium oxide has the symbol or the formula Al2O3 and iron has the symbol Fe. So this is the chemical equation. Now let's balance it. Alright, now so to balance it, let's check out how many atoms of aluminium we have. On the left hand side we have just one. On the right hand side over here we have 2. So to balance it and make everything equal, we need to add a coefficient of 2 over here to make aluminium atoms balanced. So now the next element is iron. Over here on the left hand side we have 2 atoms of iron. Over here on the right hand side we have just 1. So let's balance iron out by adding a coefficient of 2 over here to make iron balanced. How about for oxygen? Over here on the left hand side we have 3 and on the right hand side we have 3. So oxygen is balanced out. This is the balanced symbol equation for the reaction. Alright, so the next question asks us What do we call this type of reaction? This type of reaction is called the thermite. The thermite reaction. Okay, it is a reaction whereby aluminium is reacted with iron 3 oxide Fe₂O₃ in order to produce molten iron and aluminium oxide. It's actually an exothermic reaction, okay? Exothermic reaction. Exothermic reaction means it produces a very huge amount of heat. So that is it for the first question. Let's move on to the next. Now the next question says, compare the reaction described above with the reaction you would expect to see between powdered aluminium and copper 2 oxide. So if we have aluminium Al reacting with copper 2 oxide, we have two metals, aluminium and copper. On the reactivity series, aluminium is much more powerful than copper, so it means aluminium will displace copper from this compound, therefore producing aluminium oxide and copper metal. So let's balance this chemical equation. We have aluminium Al plus copper 2 oxide CuO producing Al₂O₃, aluminium oxide and copper metal. Now, on the left hand side we have aluminium, one atom of aluminium, and on the right hand side two atoms of aluminium. So we put a coefficient of 2 here to balance aluminium atoms. On the left hand side we have one atom of copper and another one atom of copper, so copper is balanced for now. And then oxygen, on the left hand side we have three atoms of copper, and over here we have just one, so we put a coefficient of 3 over here to make oxygen balanced. Now by putting a coefficient of 3 we have also affected the number of copper atoms that are present, so we put a coefficient of 3 over here to make copper balanced on the left and on the right hand side. At this point all the atoms are fully balanced. 2 atoms of aluminium on both sides, 3 atoms of copper on both sides, 3 atoms of oxygen on both sides. So the equation is fully balanced. Let's move to the next one. Alright, so the next question says, predict what would happen if you heat a mixture of aluminium oxide. That's aluminium oxide over here, and iron. So let's see the metals that we have. We have iron over here, which is standing alone, and we have aluminium over here, which is in a compound. So if these two react, what exactly is going to happen? Iron is going to come over here and try to displace aluminium, but is that possible? Let's check out which of them is more powerful on the reactivity series. So on the reactivity series, we can see the position of iron over here and the position of aluminium over here. So we can see that aluminium is way more powerful than iron. So that automatically means that iron will not be able to displace aluminium from its compound. So if we have this reaction between aluminium oxide Al₂O₃ and iron, there will be no reaction. So predicting what will happen if we heat a mixture of aluminium oxide and iron, nothing will happen. The mixture will remain pretty stable. That is what will happen. Let's move on to the next question. Now the final question says, explain why the uses of aluminium, the aluminium metal, are surprising given its position in the reactivity series. So why are the uses of aluminium like very surprising given its position in the reactivity series? Let's answer that question. We have a number of points. First point is aluminium is very high in the reactivity series, okay? If you check out the position of aluminium in the reactivity series, you would see that it is quite on the reactive side. Now you can see aluminium's position over here in the reactivity series. So it's quite a reactive metal and a reactive element. So given its position on the reactivity series, you might be thinking that, oh, this should like be very reactive, corrode quickly, and be unsuitable for everyday uses. But surprisingly, we find aluminium to be very useful for everyday products like soda cans, roofing our houses, finding applications in parts of automobiles, and so many other things that you would naturally not expect aluminium to be useful for. So, why is that? That brings me to the next point that I want to talk about, why aluminium is useful, the real reason for its usefulness. You see, aluminium forms a very thin and strong oxide layer on its surface immediately it is exposed to air. So if you have aluminium like this and you expose it to oxygen, which is in the air, you form a thin layer of aluminium oxide, Al₂O₃. So permit me to balance this chemical equation. Yeah. So, when aluminum is exposed to oxygen, a thin, strong oxide layer known as aluminium oxide forms on its surface. Now, this oxide layer sticks to the metal and protects the remaining aluminium beneath from further corrosion. This process is called passivation. That is what happens when aluminum is exposed to the air. Okay? A thin layer of aluminum oxide forms on its surface, preventing the remaining aluminum underneath from corrosion. So, what is the result of that process called passivation? So, despite being a reactive metal, aluminum is light, it is strong, and it is resistant to corrosion. That makes it perfect for many engineering uses. Uses like aircrafts, windows, frames, foils, and so on and so forth. I trust you were able to get massive value from watching this video. This has been David, the billionaire teacher, sticking around with you. If you enjoyed it, please like, share, subscribe for more content, and I'll see you in the next one.